Okay, let's start discussing a bit the phonons. So what are they? Well, if you just take any solid, it doesn't have to be a crystalline solid. The fact that it's a solid basically means that the atoms are more or less fixed at their positions. Now, if you consider the potential energy of this system, well, it will be a function of the positions of the atoms you have. And each of the atoms, they have an equilibrium point. And due to the thermal motion, they will be just vibrating slightly around their equilibrium point. So this will be equal to, if you make just a Taylor expansion, let's say Ri is equal to delta I plus Ri0, where Ri0 is the equilibrium position. And delta I is the displacement from equilibrium position. The value of the potential when everything is in equilibrium position plus the derivative. Now let me write it in this form. When all of them are in the equilibrium position times the variation plus the second derivative. And 1/2 plus possibly many other terms. Well, you see, this is nothing but the force acting on the atoms when they are in equilibrium position. But the equilibrium position itself is defined as when the force acting on each one of the atoms is 0. This is 0. So we end up having the second, we have a potential that is quadratic in the coordinates. Now let me just switch to some generalized coordinates rather than using the positions. I mean, you can say that you can just imagine the generalized coordinates as different components. So the potential of the system will be mainly some constant plus, let's say, Vij, Qi, Qj. 1/2 Vij, Qi, Qj. This will be the potential of my system. Qij of the 3n generalized coordinates. If we have n atoms, each one of them will have 3 different components, so that's why we have 3n coordinates. Well, the Lagrange Hamiltonian of the system will be just the kinetic energy plus the potential energy up to a constant. Constant doesn't change the equation of motion. But we can actually change this to an expression of this form. And each one of these alphas are called normal modes. You should have already seen the normal modes in analytical mechanics. For example, some simple cases of examples of normal modes is, let's say you have 2 masses, 2 identical masses connected by a spring. If you just pull one aside and then release it, what will happen is this one will start vibrating violently, then this one will start vibrating slowly, and then it will start vibrating violently, whereas the other one starts to vibrate not so violently. It just keeps on changing. But so this is not a normal mode. This is a mode that changes in time. But what I can imagine is I can just take these two masses, move them aside at an equal distance, and when I release them, what will happen is all these masses will just move back and forth. The system will not change. Well, it will evolve, but still the evolution will be, the motion it does will always be the same. It will not change with time. Or you can just give each one of these masses equal speeds, equal velocities in a given direction. So again, the system as a whole, the shape of the system doesn't change. The system as a whole is translated. This is another normal mode. So the normal modes of the system will be when both of the masses move in the same direction, or if they move equal amounts in opposite directions. Another example of normal modes for a three-mass system, for example, identical masses, same springs. The normal modes will be the masses on the edges, they can move back and forth in opposite directions. The mass at the center is constant. It just stays there. Or the masses at the edges move in one direction, whereas the mass at the center moves in the opposite direction. So these two masses will just go back and forth, whereas as this one goes towards the right, this one will go towards the left. So this will be the motion. A third mode is, well, all of them move in the same direction. This is the uniform translational motion. You see, here I had two masses in one dimension, and I had two modes, two normal modes. Here I have three masses in one dimension, and I had three different normal modes. So those normal modes are what is meant by this alpha over there. So this is our Hamiltonian. But you see, if you quantize this system, this is nothing but just a collection of harmonic oscillators. So the energy eigenvalues for this system will be nothing but h bar omega alpha and alpha plus 1/2, summed over all alpha. But you see, this is nothing but almost exactly the same thing as our photon gas. And these energy quanta over here are what we call phonons. In the case of the electromagnetic radiation, the energy quanta are the photons. In the case of these vibrations of the atoms in solids, they are what we call the phonons. And in fact, whatever we derived back in the case of the electromagnetic radiation, it will still be valid over here. We can write the Q potential, which will be PV over KT, will still be minus sum over single phonon states of the logarithm of 1 minus e to power minus beta h bar omega alpha, or single phonon states in this notation. I'm actually using alpha. The energy will be sum over alpha h bar omega alpha divided by e to power beta h bar omega alpha minus 1. And pressure, well, pressure is the Q potential. Basically, that's it. Just like as in the case of the photons. Now here we have a different problem though. What is that summation over alpha? You see, in the case of the photons, there is a continuous spectrum of frequencies, and we actually know what those continuum spectrum of frequencies are. But here, in the case of solids, you see here This is a simple model of a solid, these springs and masses. But you see, even in this case, the frequencies are different. They are not continuous. They will be discrete, etc. The discrete nature of the atoms will show itself. But at least in one limit, we can make certain approximations. Low T limit. We had already seen in various cases that when you are at low temperature, only small energy excitations are excited. The high energy excitations are not excited. But small energy basically means large wavelength. So at low temperatures, well, we don't really know what low T is for the time being, but sufficiently low, we will define what low T is. At low temperatures, the wavelength will be large, but if the wavelength is large, it means these waves will not see the atomic structure. So for these waves, everything will be continuous. But in such a case, the spectrum will also be continuous. It will be determined, the frequencies will be determined by the boundary conditions at the boundary of our volume, just like in the case of the photons. It will not see the discrete nature. So we can just ignore it, at least in this limit. So in this limit, we can still use the approximation, summed over alpha will still be, it was V over 2 pi squared h bar cubed d omega times omega squared over c cubed. So this was what he had derived for the photons. Well, there are a couple of things we have to take into account. One thing, I have to make a correction in this photon case. You see here I had the sum over single photons. I have to insert a 2. If I have 2 photons at the same point with the same momentum, they can still be different due to their polarization. A photon over here can be polarized in this direction or in this direction. Or in fact, any other superposition basically will just can be written in terms of these 2 polarizations. That's why I need to add that 2, just like the spin of the electron. Well, here, in the case of the photons, you see, we said that, okay, we have this solid. Every atom is fixed at their position. They can just make very small vibrations. You see, the sound can be traveling in this direction, and the atoms can be also oscillating exactly in the same direction. So this is what we call a longitudinally polarized sound. Or the sound can be moving in that direction, whereas the atoms are moving perpendicular to it. And we have 2 such polarizations. So here I should make a small correction. First of all, there are 3 polarizations for the sound wave, not just 2. And these polarizations can have different speeds. So on one hand, I have a longitudinal polarization. I can get a longitudinally polarized photon. It will have a different speed. Or I can have a transversely polarized sound waves. But there are 2 of them. 2 different transversely polarizations. So that will be one of the differences. Now the second question is, what is the upper frequency? You see, in the case of the photons can have any frequency. I can have infinitely many normal modes. But I know the number of the normal modes in the case of the sound. The number of normal modes is equal to the number of atoms I have, to the degrees of freedom I have. So I cannot have infinitely many normal modes. I should have a cutoff. There's a cutoff to frequencies. It also makes sense because we already said that we are considering a limit where the sound doesn't see the atomic structure. If the wavelength is smaller than the atomic separation, well, it doesn't really make too much sense to talk about oscillations then. So these are the two main differences in this case. This is so-called the Debye model. Well, how do you determine this omega d? This is the Debye frequency. Sum over all normal modes should be equal to, of 1 should be equal to 3n. Well, in reality, you should have 3n minus 6. But n is of the order of Avogadro. Why 3n minus 6? Because 3 of these degrees of freedom corresponds to uniform translational motion, so they will have 0 frequency. And 3 of them will correspond to rotational motion. Again, they are not oscillations, they are not sound waves. So there are 6 degrees of freedom that are not oscillations, that are not sound degrees of freedom, but 3n is so huge, you can just ignore that 6. So that omega d is v over 2 pi squared h bar cubed, 0 to omega d, dw, omega squared 1 over cl cubed plus 2 over ct cubed should be equal to 3n. So this fixes all the parameters in your model. See, the speed of the longitudinal sound waves and transversal sound waves, they are already fixed by the properties of your system. They can be measured. This omega Debye, the Debye frequency, can be determined through this relationship. Now, of course, this is this is not the simplest model you can write. The simplest model would actually say that, okay, the frequencies which is the Einstein model, you see sum over alpha can be written as, we said that they can be written in this form. Sum over frequencies. Rather than, okay, no, let me ignore this one. No. Before I had this integral over the frequencies, but it's nothing but a sum over frequencies. Well, Einstein said that, okay, let's just assume that everything has the same frequency. Well, the first approximation would be this. So you have a sum over the frequencies, everything has the same frequency. So great, you are done. You know everything about your system. Well, this Debye model is an improvement on that. It says that, okay, so at least as long as I'm in a situation in which only the long wavelengths are important, then I can just model it as photons with a cutoff frequency. Cutoff frequency because basically I cannot have larger frequencies. Larger frequencies will see the internal structure, which I'm ignoring. So these are the two models. In reality, if you consider the density of states as a function of frequency of the photons, you see Einstein model is this one. You get a Dirac delta at some frequency. This is the Einstein model. Debye model just tells you that the density, we had already derived it over here. Einstein model will be proportional to omega minus omega e, just a single frequency. This is the Debye model. Of course, here there is a cutoff. This is the Einstein model. And then you have the realistic case, an experimental measurement of a typical density of states for the phonons. Basically looks like this one. You can look at it up in your book. So it looks like the Debye model at low frequencies, because at low frequencies you don't really see the internal structure. If you don't see the internal structure, well, if you change your material, nothing will really change except the speeds. But if the speeds are more or less fixed, at low frequencies, it looks like the Debye model. At larger frequencies, you start to see variation. At some frequencies, you might not have any oscillations. At some other frequencies, you might have larger oscillations, etc. It has, okay. Typically, it will look like this. But on the average, the Debye model for most materials at least gives a reliable estimate. Because you see, you don't really need to know the exact dependence on omega if you want to calculate, I don't know, the pressure, the energy density, etc. What you need is their integral. So on the average, the deviations can also cancel out. No, you see, you can just fix that just like in the Debye model. What you do is you just count the number of normal modes. It should be equal to 3n. Well, the same should hold also for the Einstein model. The total number of modes should be equal to 3n. So that is how you fix the Einstein model frequency. Now, physically, what does that correspond to? Essentially, he's just assuming an average frequency for all the oscillators. Now, in the Debye model, this Debye frequency actually corresponds to the frequency. Typically, omega Debye corresponds to the wavelength, which is of the same order of magnitude as the interatomic spacings. So in that sense, also the Debye model makes sense, because above the Debye model, the wavelength gets smaller than the interatomic spacing. But then, I mean, it doesn't really make too much sense of a wave whose wavelength is smaller than the interatomic spacing you have. Which cuts? Well, I mean, it depends on the crystal properties, on what elements you have in your system. You see, let's see, if you go back to this case, I mean, if you have a finite number of oscillators, you have discrete frequencies corresponding to normal modes. Well, if you have many, still it will be discrete, but it might become almost continuous. So what we expect is, at least at low frequencies, at low frequencies, high wavelength, you don't expect the sound waves to really feel the crystal structure. So you would expect, at least at low frequencies, to have something corresponding to the Debye model, and that is actually what we see. But at higher frequencies or smaller wavelengths, depending on the crystal structure, it might be easier to oscillate your atoms in one direction at one frequency, but not in the other frequencies. That is why you might end up having these gaps. It just tells me that at those frequencies, it's not so easy to oscillate the atoms in a given direction. You see, in this Debye model, we had this simple case of the longitudinal and transversal polarizations. But even the direction of the sound wave might change its properties. A given crystal structure will not be homogeneous in every direction, not necessarily. For example, you might have layered structures. Sound might move more easily in one direction, but not in the other one. All those things you have to take into account, which the Debye model just gives you an approximate average description, which is valid, more correct for a large wavelength and small frequencies. Of course, if in your calculation you see that the dominant contributions comes from frequencies close to the Debye frequency, then you can say that, okay, probably your prediction will not be correct, will not be precise, will not be accurate, sorry. But if you know that the main contribution to your computation, whether it's your temperature is such that the main contribution to the energy, the pressure, etc., comes from small frequencies, then you have reason to trust your prediction. You see, rotational degrees of freedom is just 3, the total number. So, no.
Must be excluded in the Debye model.
Sure. You see, what does it mean to exclude it in the Debye model? It just means that from that 3n, we have to subtract 3 for rotations and 3 for uniform translation. We have to subtract 6. But n is already of the order of 10 to the power 23. Whether you extract it or not, it doesn't really make any difference in your model. When you are making a measurement of the phononic frequencies, well, you have a sample that is sitting over there. It's not rotating, it's not translating. Any last questions? Sure. Okay, about the exam, let's talk it in the break. Okay, so I'll see you on Wednesday.